Hello, I'm Philip Muggleston, and in this series of videos we're covering the predictive capabilities native to SAP HANA. In this video we're going to look at Kohonen self-organizing maps. Now these effectively are a neural network that enable you to cluster a dataset into distinct groups. So clustering similar to what we already saw in the examples with k-means. However, the Kohonen self-organizing maps approach is based around unsupervised machine learning. Effectively, what's different from a k-means is that the value of k, how many clusters or groups we're going to create, is not known in advance. We don't set that. The algorithm will actually work that out on its own. It will identify the most suitable number of clusters or groupings. So this approach will allow us to group similar records, and it works very well if we have a large number of variables or dimensions. So if we were to imagine the dataset we've already been using in other examples, we have customers. And for that customer information, we have actually the total spend, we have the new spend, we have income, and we have loyalty. So we have 4 variables for each customer. So we want to try and group the customers together. And if we imagine our data, we have, for example, 4, 5, in fact we have about 150 or a million, depending on the example we use, of these customer rows in our example. So this is the input data, and we want to cluster. We want to basically join the different customers together into groups. Now, how does the Kohonen self-organizing map work? Well, it's based around the concept of a grid or a lattice. So it can be either 2 by 2. For example, you have 4 nodes or 4 points in a grid, or it can be 3 by 3, or it could be 4 by 4, depending on what you choose. It's always equally sized, so it's 2 by 2, 3 by 3, 4 by 4, 5 by 5, etc. And what the algorithm does is it will place each record into a node. It will try to assign it to the most suitable node, and then it will look at other records that may be close and try to put the records that are most similar into the same node. Now, the way that works is that for each of these 4 different variables, total spend, new spend, income, and loyalty, there is a weighting. Each node has a weighting, 4 weightings, 1 for each variable associated with it. So there are 4 weightings per node. And then the first time round, for example, record 1 maybe gets assigned to this node here, number 2 here, and maybe number 3 here, and number 4 there, and eventually you may well be getting number 6 here, and number 11 here, etc., etc. So this happens, and then basically that's done by looking at what's known as the BMU, the best matching unit, which is the way of identifying, based on the weightings and the values of the different variables we've got, which is the best fit. And when we start with this, it's kind of pretty evenly spread because the weightings are pretty standard. However, the point of this algorithm is once you start working with it, the approach we use here iterates. So it goes through this process multiple times and continues to revise and optimize the weighting values and the positions of each record within the grid or within the lattice. So as it evolves and grows, and we've got 21, maybe 22 here, we kind of see little clusters or groupings of records coming together naturally in nodes. Now, not every node needs to have a record in, and it may well be there are empty nodes. It depends on what naturally fits the data. So the Kohonen self-organizing map is a way of grouping things together by taking multiple dimensions or variables and effectively putting them onto a 2-dimensional grid, and then using the weighting process to iteratively and incrementally improve the position until at the end you're left with a nice balance with records that appear close to each other being grouped together. So that's how it works from a theoretical perspective. Now let's have a look how we write that code inside the predictive analysis library with HANA. So let's first take a look at our input data. Now we've seen this in other examples. You're probably quite familiar with it now. This is our customer data. We've got about 150 customers in this example. We've got lifetime spend, new spend, income and loyalty for each customer. We've got an ID for the customers. And so we've got 4 variables, or effectively 4 dimensions, that we're going to use in our clustering. And what we want to do is to take each customer and assign them into a individual grouping based on similar customers. We want similar customers to be grouped together. So the code that we would use in the PAL to do that is very straightforward. It's similar to what we've already seen. We are going to use the algorithm in the PAL called self-org-map, self-organizing maps. So that you'll find more details, of course, as always, in the manual. So we have for this algorithm 4 different tables, 2 input tables and 2 output tables. So the input tables are our data and also the parameter table, as always. The output is 2 tables. One is actually a representation of that grid or map as a table, and the second one is the results, which effectively is for each of our customers in this case, which node, or effectively which node in that map or table, which refers to which cluster or grouping does that customer belong to. So in terms of the data, it's similar to what we use, for example, with k-means. We take the ID and then our 4 columns, our 4 variables. So that's our input data. Parameter table as standard. And then for the map table, you can see more details in the doc on this, but we just need an ID for the actual a map, which is those nodes. And then we have also a column that represents each variable. This is the weighting as described in the previous part of this video. This is the weighting that's assigned to each of the 4. So every node has a weighting for each of the 4 variables we're using. Now if you're using 3, 5 or 2 variables, then you would need to have the corresponding number of weight columns here. And then right at the end, we have something called row count, and this, you can call it what you want, but basically the last column in this map table will have the number of customers that have been assigned to that node at the end of the algorithm. In the results table, we simply have the ID, which is the ID of the customer, and then the map ID, which gives us the ID of the node, which effectively that map ID can be your cluster number. So we use a signature file, a signature table, as always, to define all that stuff. Why don't we go ahead and run it and create our procedure? So let's run, and the procedure is created. The next thing is then to prepare our input data. Now, as we've got the customer's name in the table, that's not something that we need in this algorithm. So we can easily work around that by just creating a simple view here where we have just the ID, life spend, new spend, income and loyalty from the customers. We create our tables for parameters, the map and results. Map and results will be empty. And what I'm also doing here to make it a little easier, because the results just contains the ID of the customer and the ID of the map, the segment number, is actually to join this result, this segment number, onto the rest of the data, so we can see the loyalty, income, new spend, life spend, and customer name, as well as which cluster they belong to. This is what we did with k-means. It's a very similar approach. So just a quick join to make things easier to understand. Now, in terms of the parameter table, we do have 4 important parameters. Thread number, you know and love. This is a performance optimization. Set it to an appropriate number of threads based on your hardware, what's available. The size of map parameter is very specific to the Kohonen self-organizing maps. It basically says what will the grid be, and if a value of 2 means it's a 2 by 2 grid, so you'd have 4 nodes. A value of 3 here would mean a 3 by 3 grid where you would have 9 nodes, or if it was 4, the value would be a 4 by 4 grid where you would have 16 nodes, and vice versa, and so on. So set this to the number of the size of the map in terms of the number of the width and the height of the grid or the lattice. Because this algorithm is based around starting with something and then continually improving and improving and iterating, you can also specify how many times the algorithm should iterate. Now, it depends on how long each set of data you've got takes to settle down. So this, you could need a small number would be fine, a large number would be fine, but obviously this number impacts performance because the more iterations you do, the longer it might take. Finally, we have something called normalization, and this relates to how the values are adjusted each time you perform an iteration. You can have no adjustment, that's what we use here. If you want, you can actually have the values changed each time to say put them between a value of -1 and +1, or you can do something based on median standard deviations with the Z-score approach. That's more detailed than I'll show in this video, but be aware that in the manual you get lots of details on some optimizations here of how that algorithm can work. So we've now done that. Why don't we have a go and run this? So let's create and update our parameter table. So we run that code, and now we're ready to go. So first time we've got empty tables anyway, we can run the code. Okay, it ran very quickly. Of course, this is HANA. Even this is a relatively small volume of data, but if we ran it on 1,000,000, it would run very quickly. The actual algorithm here, let's just refresh the tables. The algorithm that HANA's using here is iterative. It's very processing intense. It's doing effectively a lot of passes, a lot of iterations around a full grid. So that's something that's very well suited to doing in memory, particularly if you have a large amount of data, a lot of rows, or you want to have in your table, or you want to actually have a grid that has maybe a large number of nodes in it, maybe a 10 by 10 or whatever you want to do. So let's have a look at what we've got out of here. We've got the map table and the results table. So if we just have a little preview of the map table, here we can see we set a 2 by 2. That's what we were going to do as the map size. So we get 4 different nodes because 2 by 2 has 4 nodes in it. We get the final weightings for each of the 4 variables, and we also get the number of records or customers that have been assigned to each of these map nodes. So we can see that actually for ID2 we have 97, for ID3 we have 53, and none at all for 0 and 1. So it sounds like this data we're working on here naturally fits into 2 different groupings. That's how the data just naturally fits together, which makes sense. We kind of saw that already with the k-means. So that's one example we've seen. Maybe we want to change that and tweak that a little bit. For example, we could change the size of the map. So just as part of my runtime here, maybe I update the parameters to say let's have a 3 by 3 map. So set size of map to 3. So we'll get 9 nodes this time. So maybe we run that. So we can just empty out the map and the results table, and we can run that. This time, again, it runs very quickly. When we look at the map, if we refresh, we will see this time we've got 9 different rows because we've got 9 nodes. We've got the final weights for them, and this time we've got the number of customers that were assigned to each of those nodes. So we can see this now, the clustering has changed significantly based on giving it a different grid size. And what we also might want to do, for example, if we might want to change the number of iterations and say, well, iterate it a few more times. Don't do it 100, but do it 1,000 times or 10,000 or however much makes sense in your case. So again, we could update, we could clear out the tables and run the algorithm again. This time it ran 1,000 iterations, but again, very quickly to run within HANA in memory. So here we can see now we've run more iterations, and actually the number of customers assigned to each of the nodes or each of the clusters effectively has actually changed and evolved a little bit, and that's because we just let the algorithm settle down by running more and more iterations. What we can also do is look at the results table. So if we go to the results here, we can see that for each customer ID we can see which map node they were assigned to, which effectively gives us the cluster number. But that's kind of a bit raw on its own. What can be more interesting is if we go to the view that I created, and if we go and look at our views, we can see we have here all 150 customers with all of the 4 variables and the cluster number that we've assigned, which is effectively the ID of the node within our self-organizing map. And then we can do further analysis. For example, look at the distinct values. Well, we kind of already saw that by customer, but we could maybe see cluster number, we can see how many different customers have been assigned to each cluster number, what the distribution is, etc., etc. We can perform more analysis. So that's a self-organizing map. It's a very good way of performing clustering. It's using more of a machine learning approach, unsupervised machine learning based around a grid or a network, and it's a good way of clustering. It gives us an alternative to using k-means, and it's available right now in the HANA Predictive Analysis Library.